So no, are we done?
No.
No, we're not. We want it when t equals 0. So can we have t, we can plug, oh, it really doesn't like being inside there, I think. Hold on. Do we have just t's in there?
Nope.
What else do we have? But do we know what x is in terms of t? So at this time, x is going to be sine of 0, which is what? And y is going to be cosine of 0, which is 1. So you just plug all this in and you end up with 0 plus 3 times 2 cosine 0, which is 2, plus 0 plus 0 times negative sine of 0. So you end up with what? 6. You're done. Just be careful. You need to answer the question they're asking. If they ask you for just dz dt, you're done. But are they asking for just dz dt?
No.
No, they're not. No, you're absolutely right. I should be consistent, especially at the beginning here.
Yeah, I'm really confused.
Yeah.
Why not the bottom?
Why not the bottom ones? Oh, you're absolutely right. Oh, man. Jay is just slamming me here. Yeah. Now, look, the next level is written in terms of multiple things as well, correct?
Yeah.
So what am I going to have to do with each of the bottom ones? So ready? I'm just going to cheat a little bit here. Okay, done.
I have a question for you.
Yeah, go ahead.
How did you take a partial derivative of a single variable
Same
function?
thing. So let's finish. So what would the final answer be? dw dv. It would be dw dx times what?
dx dv.
Dx dv plus w dy times dy dv, or delta, sorry. Next one is what? Delta z times what? V delta v plus
Delta
t
times delta
t
t
delta v. Yeah. So does this expand very quickly?
Yeah.
Does it get a little bit nasty? Yeah, it's not that bad. Yeah,
Does the black thing there?
the black thing there.
Yeah, before the equation. Is it delta or derivative?
I don't know what you're talking about.
DWDT.
So be very careful. Make your tree. Make your tree. Write it out. And be very careful. See what you can get. It looks like this. It's kind of cool.
Whoa.
It goes like that, actually. And that's supposed to be at the origin right there.
In 3D land?
No, in 2D land. In 2D land, if you graph all the points, it goes whoop. It is symmetric across y equals x. Now, the point is, how many functions do you need? Well, you need at least 3. For example, you could break it apart into like this, right? And then you would take that section, and then you would take this section. Now, here's the thing. You have done this before where you have separated things that are a little bit similar. For example, let's say I gave you, what's this? X squared plus y squared is equal to 4. What is that? Circle with radius 2. Now, could you isolate y?
Yeah.
Yeah. Well, you know that's y is equal to plus or minus the square root of 4 minus. So you could differentiate the top. You could differentiate the bottom. Let's say I asked you for the slope of a tangent line at a certain point. You could isolate. You know automatically if it's on the top of the arc or the bottom. So you can separate this one. So theoretically, maybe you could separate this folium. Technically speaking, isolating y in this is the equivalent of solving a what?
3.
Okay, I'll give you a hint. Not a quadratic. Not a quadratic, but a... What's 1 degree higher than a
I don't
quadratic?
know.
A 5 dread.
The cubic.
Cubic, thank you. Quadratic, cubic, quartic, quintic.
Sextant.
Yeah, I think yeah. But the point is there a general formula for any cubic?
Yes.
Yeah, there is. Is it really nasty?
Yes.
Yeah, it's terrible. It's terrible, terrible, terrible. So do you ever want to use that?
No.
Okay, so if you were going to do this in Calc 2, by that point you've done what topic? Not explicit.
Implicit?
Implicit, what's that? Implicit?
Differentiation.
Yeah, implicit differentiation, right? Where you would go 3x squared plus 3y squared y prime is equal to 6 times, you'd have to use the product rule, derivative of the first times the second plus the first times the derivative of the second, and then you would isolate what?
Y prime.
Y prime. You've done that a ton, right? You've done that a ton. And you do that specifically because can you separate out y?
Not easily.
Not easily. There's your good word. There's not easily. Okay. So, what happens in multivariable calculus land?
We use partial.
If you look at those two things. So we did this out, we used implicit differentiation, and we're writing the original equation right there. Once again, if you want the proof of this, go take a look at it. I'm not going to prove it for you, but this is what it says. If you have a function f of x, y, and you set it equal to 0, you do this all the time. Historically, why have you set things equal to 0? So you can do what with it?
Solve it.
Why do you set it equal to 0?
Get rid of
Zero is easy to solve for.
No, you set it equal to 0 because of the zero product principle, meaning if two things multiply together, at least one of them has to be 0. You set things equal to 0 so that when you factor that side, you have a bunch of small things multiplying together to equal 0. You've done this over and over again. Can you make any equation equal 0? Yeah, just toss everything on one side, right? So if you have something in terms of x and y, does it matter if it equals 0? No, because what can you do?
make it.
Put everything on one side. Check the proof out in the book if you want to understand why. It's totally okay if you don't. But the point is, if you have something in terms of x and y and it equals 0, and you want to get the partial with respect to x, what do? You take the partial with respect to, so you want to get dy dx, you do the partial with respect to x of the original function, partial with respect to y, and the only thing you add in front of it is a minus. That's it. That's it. So let's do one.